Welcome to Ask and Learn.
Large research balloons containing 2 times 10 to the 3 meter cubed of helium gas at 1 atmosphere and at a temperature of 15 C rise rapidly from ground level to an altitude at which the atmospheric pressure is only 0.9 atm. Assume the helium behaves like an ideal gas and the balloon's ascent is too rapid to prevent much heat exchange with the surrounding air. Calculate the volume of the gas at higher altitudes, the temperature, and what's the change in internal energy of the helium balloon as it rises to the higher altitude. Okay, so I want to approach this question. The basis of my approach for this question will rely on the fact that it doesn't permit much heat exchange with the surrounding air. So Q equals 0. So I'm taking it to mean that it's adiabatic, and I'm applying all of the formulas from the adiabatic section of the book. So now that I have the general strategy that I'm going to use down, I'm going to write down the givens. One thing that makes me hesitant about this strategy is that this problem is rated with 3 dots, and I personally wouldn't rate it in that way if this is the way you're supposed to solve it. So it's possible that I am missing some subtlety, or maybe not. I don't know. So I'm going to write down these givens. And then let's see. Okay, and it's helium. So you have CV is 12.47, and then you have your gamma is 1.67. All right, let's box away these. Oh yeah, what is this? Joules per mole Kelvin. Do I have all the other units? Yes. Okay. Okay, so the first part asks for what? I think it asks for the final volume, right? I'm just gonna double check. Yes, final volume. Okay, so to get final volume, you want to use P initial, V initial to the gamma power equals P final, V final to the gamma power, just straight from the section on adiabatic processes. If you rearrange this formula algebraically, which I'm going to skip because these videos, I'm trying to keep them short, P initial or P final to the gamma, to the 1 over gamma, and then this should be V initial. Great. And so we know that P final is 0.9 and P1 is 1. So then the ratio of that is going to be 1 over 0.9 to the 1 over gamma. So 1 over this 1.67. And that, again, just comes, I forgot if I said it, it comes from a table in the book. And then that's 2 times 10 cubed meter cubed. And there were more sig figs on that. There was 2.00, but I'm not going to write them. So anyway, if you stick this into a calculator and keep the 3 sig figs, I think all the terms have, they don't all have 3 sig figs, but I'm going to use 3 sig figs anyway. Because the 0.9 only, I think that's only 1. I don't remember how many zeros were in the book, but okay. Anyway, so it's 2.13 times 10 cubed meter cubed. So not a huge volume change. Box that up. And B. So B asks for the final temperature, I believe. I'm just going to double check. Yes, calculate the temperature. And so you have another equation in that same section of adiabatic processes that relates temperature and volume. This is that equation. And then you want to, so if you algebraically manipulate this and solve for T final, then you got T initial times V initial over V final to the gamma minus 1. And if T initial is 15 degrees C, we don't have to convert it because our final answer is going to be in C. So we're not kind of relying on units coming together and canceling and stuff. Using SI to make sure our answer is in SI. So it's fine to do that. So then we have 2 divided by 2.13 meter cube. Oops. I think this was times 10 to the 3 meter cube, but kind of running out of room. And then for the ratio, that would end up canceling. And then that's just your 0.67, 1 minus 1.67. And then you get 14.4 degrees Celsius. So it cools just a little bit because it's expanding. So it's expanding a little bit, cooling a little bit, kind of makes sense. And then for part C, we want to get the delta U, and that's N CV delta T, but oh no, we don't have N. Let's go ahead and kind of just do like a little bit of a side calculation for N. You can use that with the ideal gas law. So you have PV over RT is N. So let's just use all of our initial values. This time we do have to convert temperature to SI because we're kind of doing this thing where we're like, well, if we use all SI, then the answer's got to come out SI. Without actually explicitly canceling the units and breaking it all down to meters, seconds, all the base units. Okay, so 1 ATM times 1.01 times 10 to the 5 pascals per ATM. Okay, I'm just gonna like erase some of my little border. So I'm running out of room with all these unit conversions. All right. Multiplied by 2 times 10 cubed. And then this whole thing, oh wow, this is getting so messy, but hopefully I can recover. Okay, and this whole thing is divided by 8.31 times 15 plus 15. I really should have done this on a different one. Or maybe I should convert all the units before I stick them in the equation. Okay. Wow, that's like so messy. I'm just gonna, for anybody that's like deeply confused, I'm just going to do this on a separate page, and then I'm gonna have all the room that I want. Okay, this whole page is dedicated to getting N, and I will use the same symbol. N equals PV over RT equals, oh, so much room. 1 ATM times 1.013 pascals per ATM times 2 times 10 cubed meter cubed, all divided by 8.31 joules per mole Kelvin times 15 C plus 273.15. And this puts that whole thing in Kelvin. Degree C. Okay, great. And then if you plug this into a calculator, you get a huge number, which kind of makes sense because the volume's huge. So you get 84,700 moles. All right, now you can go back to our first page and just kind of plug that in there. Great, so now we have everything we need to get the change in internal energy, 84,700 moles times 12.47 joules per mole Kelvin times delta T, so that's 15 minus 14.4. You can subtract degrees C, and it's the same difference as degrees Kelvin. And then, oh no, I'm back to being squished. 634 times 10 cubed joules. And really not enough room for a box. I'll just do a partial box. Oh, there, that worked. Okay. So there's our answer.